If we want to find instantaneous acceleration, we can start with our understanding of average acceleration, which is the change in velocity over time. And then we can shrink that time interval until it gets really small. So if we consider, for example, between time 1 and time 6, there's some average acceleration here, which is the slope on this velocity versus time graph. And then you can shrink it to an interval between time 2 and time 5, or time 3 and time 4, and keep shrinking it until you end up with a very, very small time interval here, right centered at time 0. So we can let that time elapsed get tiny, which as an equation looks like this. We say the acceleration as a function of time is equal to the limit as my time interval goes to 0 of my final velocity minus my initial velocity divided by that time interval. And that becomes a derivative. So as we take this limit, we get the derivative with respect to time. So this is my acceleration as a function of time is the derivative with respect to time of my velocity, or a is equal to dv dt, derivative of velocity with respect to time. So to summarize our kinematic relationships between position, velocity, and acceleration, my velocity is equal to the time derivative of position, or dx dt, and my acceleration is the time derivative of velocity, or dv dt.